This is Brian DM82 and I'm making a video on the Chronos using it with the USB dongle and Anarin's RF booster pack. Right here's some code and processing that I wrote for the USB dongle. Up here just defining some basic commands for it. Reset, status, get product ID, start and stop simplicity iStack. Then there's sync. I just added that in today. Took me a while to get it right, but it's good now. At least for getting the watch status and stuff. I didn't do data logging and stuff. That's a little bit more complicated. For sync, if you send sync send commands, you can use one of these commands down here. The only one that I use is get status, which gets the watch time, date, and stuff. The NOP command is probably pretty worthless because the USB is already sending it. As soon as the Chronos sends the AP a ready to receive byte, the AP automatically replies back with the NOP, the no operation, just telling it to wait a second. Then the Chronos will send another ready to receive byte, and if you've sent one of these other commands, it'll throw that in there instead of the NOP, and then the Chronos will send you back the data or whatever. Right here's some hardware state definitions. All this stuff right here is basically copied out of the code from the control center. Let's see. For the baud rate, I set 9600 bits per second. They use 115200. I just think 9600 is a little more stable. First thing I call is initialize. And initialize. It resets the software stack, or resets the access point, the USB dongle. Starts and stops simplicity I twice, because once you start simplicity I, it says it's trying to link. Then if you stop it, sometimes it won't be stopped. It'll say it's still trying to link. So I call stop twice just in case that happens. And then I reset the AP again, call get ID, which just returns the AP's ID address basically, and then the status, which is going to say hardware idle. During the onDraw method, there's just a couple Boolean values here that let it call either get data, which gets the accelerometer data, or get watch time, which is for sync mode. Basically, when you run the program, you just hit a letter, A, S, or K for accelerometer, sync, and then to kill it, it'll kill both the modes. Down here, commented, I have more modes that you could test out. Basically, just individual functions. Right here is the send receive packet function. It's the main function that everything uses. You send the command byte, which tells it what to do. Then you send the length, and if it's sync, you're going to be sending data for that second command that you're sending. For a packet, the packet start is the start marker, FF. Following that is the command, and then the length of the whole packet. Now, if you send a length byte of 4, it'll return these three bytes plus the byte that you're looking for. So basically, whatever you send it, it'll send the same amount of bytes back. Right here is just basic functions. Get status, it automatically switches the return byte and picks out the right hardware state. And then simplicity I start and stop. Get data. This reads the first status byte and switches it out and picks between the hardware states. It has the modes ACC, PowerPoint, not PowerPoint, PPT. Yeah, that probably is PowerPoint. Then defaults unknown. You'll never get unknown. Buttons, and then XYZ accelerometer data. Right here, BM sync start. In the code, they have it commented out, so it really don't do anything. It's probably worthless to even call it. If you want to use sync, call the start simplicity I, and that'll start the simplicity iStack, and sync runs off of that. I don't even know why they got the command in it. Then there's get status, get buffer status, read buffer. Call get status first, then you can call get buffer status, And once I think it returns a 1. If it returns a I think if it returns a 1, that means that you can read the buffer. There's actually something in the buffer. So call get status, check if buffer status equals 1, and then read buffer. Right here, the bytes, see how it says byte 1? That means that I only want 1 byte back. And, it'll actually return the 3 header bytes and then give me my 1 byte. Even though I put down a for loop, I already know that it's only going to be one byte. I don't even know why I put that loop in there. Read buffer is the only one that needs it because I request 19 bytes returned, and it'll increment through each byte. Get watch time basically gets the data. Right here's the main function: start sync, start ACC, and start ACC or PowerPoint mode, and then down here is kill modes. And these basically just reset the AP, start the simplicity TI stack, and set the Boolean value that runs in the onDraw method. So I'm going to start this right now so you can see what it looks like. Damn little dongle. Alright. Alright, so here it is right here. Let me get this thing pulled up. Put you back over there. Alright, now I'm going to hit A. And then I'm going to start my watch in ACC mode. Okay, now it tells you accelerometer data, hardware or mode AC. When I hit a button, shows you the buttons that were hit. So now I'm going to cut this off, press K to kill the modes, then I'm going to start it up in sync mode. And right here, sync mode. As you can see, the time 3:07, 7 seconds, whatever. Date, alarm, temp, altitude. Now the only thing that changes right here is the time itself. While you're in the sync mode, temperature and altitude remain the same. Right here's the code for the Anarin booster pack connected to the Chronos. This is just a demo. It's just going to draw some ellipses on the screen, showing the button presses, and then some dials for the accelerometer data. It's also going to show the watch address, the booster pack address, signal, and the mode that the watch is in. Down here for the accelerometer values, it tries to stabilize it a little bit. That way the dial doesn't keep slightly moving back and forth. You can actually hold it steady and it'll stay steady. So I'm going to play this. Start the watch in ACC mode. Okay, and yeah, just some dials up there. So whenever you move the watch, it changes the dials. Shake around or whatever, and it shows the signal. That's not an actual representation of the signal. I just changed it around, made it a little shorter. That way you can actually see it moving. The signal for this thing is actually great. I've never actually had it go out on signal on me, but that's just going through about 3 rooms. But that ain't bad for an RF watch. It's better than Bluetooth. So I can hit the buttons and they'll just light up, showing which button I hit. And then I'm going to kill it, and then it's just going to go back to being blank. This is the next version of my code for Anarin's booster pack to connect to the Chronos. I updated it, allowed it to check the destination address. That way you can put 2 of them next to each other, and it'll be able to see which destination it's actually going to, if it's going to one booster pack or the other. And because it already reads the watch's address, it can filter out between watches too. It knows which watch that it's working with. Okay, besides that, I added in the transaction ID. That way you can filter out duplicates. Because I also wrote code for a range extender that you can use. Since you get 2 booster packs in a box, I just wrote code to put the other one to use. Alright, but anyway, this is what goes on. The Chronos, the end device, sends a join request. the access point, the booster pack replies. Then it sends a link request, access point replies, then it just keeps sending data, being the accelerometer data. Alright, now the join request, the Chronos join request. First byte, that's 19. That means that there's 19 bytes following that one, following the length byte. Next 4 bytes is the destination address. This is eventually going to be the AP's address. Right now it's all F's because it obviously doesn't know who it's communicating with. It's just sending it out just to see if anybody replies. The 4 bytes following that is the watch address. After that is the port. The port, I use it to determine the mode. If it wants to join, it'll have the 3, link 2, and then I give it the port 20 to tell it to start using that port to reply back to the AP. This right here is device info. A 0 over here means that it's a end device. The last 3 bits on this side means the hop count. The hop count gets decremented every time it's resent by a range extender. That way, if you have like 3 range extenders in close proximity, this message doesn't get sent around forever. Next byte is the transaction ID. So as you can see, it starts off being C3, goes to C4, C5, C6, C7. That's an important byte because let's just say, yeah, you got those 3 range extenders. Now, they're all resending basically the same data. The hop count's going to kill it eventually, but at one point, all 3 of them are going to be sending the same message right around the same time. Now, the Chronos has to be able to decipher, the Chronos and the AP have to be able to decipher which transaction is just a duplicate, and they do that by looking at this transaction ID right here. If it's the same thing, if they've already read it before, or if it's lower than the current transaction number they're supposed to receiving, they know that it's a duplicate. And if it's the same, they know it's a duplicate. And if it skipped one, they know if they missed a packet. 6, this is basically 0-1 means it's a client request. 8-1 server reply. The next one, C5. That is another transaction ID. As you can see, Chronos sends out C5. The AP replies back with the same transaction ID over here. That way it knows that it's replying to this transaction. This byte right here is the join token. 5, 6, 7, 8 is the join token. It's written least significant byte first. So it's really read 5, 6, 7, 8. And then C back here, that is connection number 1. There's only going to be one connection. The last one, 2, is the protocol version. Okay, then you got the reply, join reply coming from the AP. First byte, length byte, that's 18. And it sends out the destination address, which is going to be the watch's address, and its own address. 1, 3, 4, 5, 6, 7, 8. Then it sends out the port, 3, device info, its little transaction ID, and then it sends out, yeah, this is server reply. It repeats the same transaction ID from the one before it, and then it sends out the link token. The link token is dead beef. DEADBEEF. That last byte there, see, what is that? Encryption. No encryption. Next, the Chronos sends the link request. First byte, linked byte, the addresses. The port 02 means it's a link. Just sends back the same link token. The AP replies. And the most important thing in here is the 20, which is the port that it wants it to use. So then, as you can see, as soon as it gets that, it starts using the destination address as the AP and using the port that the AP told it to. Okay, and I got all this on commented right up at the top if you want to check that out. The ED, the end device data. First byte, the button and the mode. The higher nibble is the button press, the lower nibble is the watch mode, either ACC or PowerPoint. The next 3 bytes is the accelerometer data. If it's in PowerPoint mode, they're all going to be zeros. So right here is basically what this program has to do. Wait for the ED join request, check the join token, copy the transaction ID and source address, and then reply. Then it waits for the link request, copies the addresses, transaction ID, and then replies. Then it just basically keeps waiting for data. And it checks its destination address to make sure that that watch is communicating with that specific booster pack. Let's see. Right here is just a sample function for getting the data, deciphering the data that the booster pack sends to it. I've got that in the Anner and Chronos demo though. Right here, destination address, you can change it if you're using multiple ones. I used to have it hard-coded into this little join and link arrays, the little generic link arrays. But I took it out just so you could change it easier, and so I can access it easier whenever I'm sending it out and stuff like that. Now these arrays right here, the data array, that's just a general array that I use to talk, basically communicate with the radio. The join array, as you can see, it's mainly filled with zeros, but it's basically a placeholder. I'm going to add in the destination address, the watch address, and then this booster pack's address for the source, and then send that right back out to the Chronos. And same with the link array. Update the addresses and the transaction IDs, which are right here. These zeros right here are the transaction IDs. 81, signifies server reply, and it's going to go with the transaction ID, which I'm going to be incrementing every time I make a transaction. And then these are going to be repeated transaction IDs from the Chronos. Receive data. This array right here, I basically just fill it up with the data that I'm going to be sending out through the UART. Custom config, the first byte is reserved. Reserved for, I'm just going to be copying a command in there. It's most likely going to be the write to transmit FIFO command. Just makes it easier. Um, 30, this one right here, this controls basically the main bits in this one is you can set the radio to automatically go into transmit mode after receive, or receive mode after transmit. I don't like to use it because it just doesn't work half the time. I don't know if I have to pre-fill the transmit FIFO or what, but it's just easier not to use it. Alright, some variables. Radio transmit, just set it to enable the radio transmit mode. Radio set, sets the radio state to transmit or receive, depending on this radio transmit byte up here. Data TX, I'll set that if there's data waiting to be sent out the UART. Idle, there's a timer that lasts for 5 seconds. It'll set this until the booster pack that it's been idle for a while, and it needs to reset the frequency synthesizer, because if it's not reset, eventually it'll start drifting and it'll get inaccurate. This writing right here is a new one that I added, add TX. It's just somebody requested the address transmit. So just check that, set that, and it'll send out the address to the UR. Previous transaction ID, this looks to make sure that there's no duplicates. Then the transaction ID. Right now it's set to 0, but I'm going to set it to a random value based off the signal strength later on. Right here's some functions, UART transmit byte, SPI transmit and receive. The SPI, it works by you send out a byte and it gives you a byte back. So if you want to transmit something, you send it the data that you want transmitted and it's automatically going to receive a byte, and you just discard those bytes that you received. And if you want to get something back, you just transmit dummy bytes and then you save whatever's received. Radio write, radio read status. To read a status register is kind of different from just regularly reading a register. The status, it fluctuates, so you want to read it multiple times until it stabilizes. Okay, so here's the main function. First, set up the clock, set it to 8 megahertz. Set up the idle timer. This will wait for 5 seconds, then it'll let it know that it's idle. Reset everything. Right here I'm setting up the UART 833. I'm setting the baud rate to 9600 bits per second. I really don't send it anything faster because right now I need to put a delay loop in it anyway. I don't understand why, but it needs a delay loop. If I send it too fast, it'll start duplicating the bytes that goes out. I'll have to look at that UART transmit routine to make sure that I'm doing it right. Now I just set up the ports, set up the output, red LED, UART and SPI, and then the clock. Set up the SPI, set it up 3-pin, even though it's technically 4-pin if you include the CSN pin, but I just handle the CSN pin myself. The baud rate set up for 100 kilobits per second, and it can be set up to 600, but I've set it up to 500 before, and it just isn't stable. I don't know why. It just it operates better on 100. 200 works good, but 200 is probably the highest I would go. Okay, right here, set up the initial configuration registers. Set up the power, enable and calibrate the frequency synthesizer. Right here's where I set the transaction ID to a random value. Right here, radio set. This right here, if you set radio set, it'll turn the radio into transmit or receive, and then it'll clear the byte. That way the next time it runs, it doesn't automatically set it to transmit or receive again. Data TX. Now this is sent. Whenever you set this, it's gonna send whatever's in the ARCS array out. And after it sends it out, I set a bit so that the next read users know that it's been read before. Basically, you read it and you know that you've already read that data if that bit's present. The address TX. This is what I just added. Basically, you request the destination address by sending it a value of BB, and it'll send you the address back, the address of the booster pack. Right here, it goes into low power mode and just waits. Now, whenever it receives something, it'll wake it up, or if that idle timer expires, it's going to wake up, set it to idle, then it's going to calibrate the synthesizer, and basically restart the radio in receive mode and just wait until it gets something. Right here's the GDO interrupt handler. It clears the idle timer, so anytime it receives something, that idle timer basically gets reset. And right here, as soon as that GDO pin goes high, that means that it's getting data right then. Now you want to wait for this to go back low before you check the data, because it's not going to be finished receiving all the data yet. So I flip the state, or I flip the edge select, and I wait for it to go back down low before I actually check the data. Okay, right here, if not radio transmit. Um, because if it's transmitting, it's going to set the GDO pin as well. And basically, if it's transmitting, all you want to do is just clear the radio transmit. That way you know that the data's been sent. Um, let's see. First thing you do is read the first byte in the FIFO to get the length. Because it's variable length packets, you need to know the length, obviously. So you get that, and I basically filter it out for 20 to 15 bytes, because that's what ACC and PowerPoint data and the replies and requests, they're all going to be 15 to 20 bytes. So I don't care about anything else. If it gets, sometimes it might get some random transmission. The odds are pretty great, but it's possible. Data array 3F. Get the rest of the data. So right here, I just get the rest of the data out the receive FIFO, including the signal status and the CRCO kbyte. And right here, I check that CRCO kbyte, and I make sure that the previous transaction ID doesn't match this one. If it does, that means it's a duplicate, and I'm just gonna clear out the FIFO. Right here, I set the current transaction ID as the previous one. That way, next time I know if it's a duplicate or not. Now right here's where I check the port. If it's 3, the end device wants to join. So I'm going to check the join token, make sure that's right, and then I'm going to modify that join array. I'm going to put the source address in it, which is the watch address. I'm going to put that in the join array, and then I'm going to put the destination address, which is the booster pack's address, in there. Then I'm going to set the transaction ID. I'm going to copy their transaction ID and send it right back. That way they know that I'm replying to it. Then increment our transaction ID, flush the transmit FIFO, and basically transmit that join array. Now if it's port 2, the ED wants the link. I check the link token, modify the link array, send it right back out, just like in join. Right here's whenever it sends data, here's where I check the destination address, make sure that it matches up, make sure that it's addressed to this booster pack, and then I send out, or not send out, but I copy the data, such as the buttons, the watch source address, and the signal strength. And then after everything's all said and done, I clear out the receive FIFO. Right here I was telling you, if it's radio transmit, just clear the bit. Then I set it back to 1, because after it receives or transmit, the radio state's in idle. So I set the radio set bit, or byte I should say, and it will reset the radio back in receive mode. And then I reset the edge select, clear the interrupt request flag, set the edge select back to low to high. Right here is UART transmit byte routine. So not only do I have the problem with it taking too long to send stuff out or duplicating bytes, if I don't clear the UART receive interrupt enable flag, if I transmit something, it automatically sets that off, which means it thinks that it's receiving data. Just another quirk to it. I don't know exactly. Right here's the SPI routine or function. Radio write. Whenever you write or read something, you can do it in bursts, and it'll put each byte into its consecutive address location. Now for reading a status register, you cannot burst read a status register. Because status registers share the same address locations with commands, this burst bit is basically used to determine if you're reading a status register or you're sending a command. Right here's that idle timer interrupt routine. Toggles the red LED, clears the flag, and wakes it up. Tells it to restart the radio, basically. Right here's the UART receive interrupt. Just makes a copy of whatever's in the buffer. If it's FF, it will set a flag data TX that will send out whatever data that it's got stored from the Chronos. And if it receives a BB, it's going to send out the address, this device's address. Then it's going to wake it up, have it send it, and then it's going to go back into receive mode if it needs to. Right here's the radio read status. This loops, looks like 3 times, and it tries to get it to return the same byte consecutively. That way it knows that everything's been stabilized and that's the correct value of the register. If it returns FF, that means there's an error. This is the code for the range extender. I haven't personally tested it out yet, but it's pretty similar to the Chronos Air code. The main difference is it sets the main clock to 16 megahertz, there's no UART, and it sets the baud rate at 200 kilobits per second. All it does is receives whatever it can get and transmits it right back out. If you want the code for this and the processing code of the Chronos Air code, visit my blog at briandm82.com. You can also check out my other projects that I'm working on.